Hi folks, we're going to take a look at number 22 on page 158. So let's take a look at the question. It says that the printed area of a page is going to be 81 centimeters squared, and we've got margins on the top and the bottom. That'll be 3 centimeters. So here we see 3 centimeters, and then on the sides 2 centimeters. They want us to figure out the dimensions that will minimize the amount of paper. Okay, so what we're trying to minimize here is going to be the area of the whole sheet of paper. And because of that, it probably would be tempting to call, say this X and this Y, or this length and W, and use those as your variables. But I'm kind of foreseeing a bit of an issue, and it has to do with the information that they're giving us, this 81 centimeters squared. So I'm just going to draw a separate diagram here. Let's say we did do that. So let's say we called this X and this Y. When I want to use the information that the printed portion has an area of 81 centimeters squared, well, what I'm going to have to do is this is going to be this area 81 is going to end up being equal to, well, X minus 2 and 2 is 4, so X minus 4, and then here Y times Y minus 6 to represent the length and width of that smaller rectangle. And then I'm going to have to use this to isolate one variable in terms of the other. All right, and you see that that's going to be a bit of a mess. It's certainly doable. I can isolate Y in terms of X or the other way around, but it's going to be more complicated. Whereas if I call this X and this Y, 81 equals X times Y, much easier to simplify. Okay, so sometimes what might be the more obvious thing to do isn't necessarily the best thing to do. Okay, had you solved it the other way, no problem, but I think here I'm going to call this length here X and that length there Y. All right, so now when I'm trying to find the area of the large sheet of paper, well, again, it's length times width. Here the length is just going to be X plus 2 plus 2, so X plus 4. Okay, and then the width of the whole sheet of paper is just going to be Y plus 3, so times Y plus 6. Okay, and so this is the model that I'm going to use. All right, like I said, had you done it the other way, it would have worked perfectly well. It just would have been a little more work in terms of simplifying the equation. All right, so now, again, I've got my two variables. This is where now I can take 81 equals X times Y and isolate one of these variables. So I can do either one. There isn't one that's easier than the other, even when I input it. So just for the fun of it, I guess I seem to like having X in my equations, so I'll isolate the Y variable. Okay, so now, in fact, so let's put that in. So X plus 4 times 81 over X plus 6. Okay, now here I could take the derivative of this function, but it would mean using the product rule. This is easy enough to multiply out that I think it's worth distributing and then taking the derivative. Okay, so X times 81 over X is just 81 plus 6X, okay, plus 4 times 81 over X, so 4 times 80 is 320, so it'll be 324 over X, and then plus 24. All right, and let's think about what our range is going to be here. So our domain is going to be, well, here I know I need X to be strictly greater than 0. All right. So let's now take the derivative. All right, so here we've got derivative of 81 is 0, derivative of 6X is just 6. Here, this is 324 times X to the negative 1, so it's going to be negative 1, so negative 324 times X to the negative 2, so that'll just be X squared in the denominator. Okay, and then here plus 0. Okay, oh, sorry, that's the derivative. And so we're going to do what we usually do here. Let's set the derivative to 0. Okay, multiply both sides of the equation by x squared. So I'm going to end up with just 0 here, 6x squared minus 324. And now let's solve for x. So bring the 324 to the other side, divide by 6, and then take the square root of both sides. And of course, since x is a measure of length, I don't want the negative one. Okay, so this is an application question, so we'll find an approximation. So 324 divided by 6, okay, and then square root of that. Oh, sorry, I'm going to do exponent 0.5, and we get 7.35. Okay. Now, of course, what we need is to check that this is indeed an absolute minimum on our, or gives us an absolute minimum on our domain here. So I'm only interested in greater than 0, 7.35. So let's take 1 and let's take 8. All right. So 1 will be very easy. That's going to be 6 minus 324, which is just going to be negative. And then here, the other one, I guess we'll check. Okay, 6 minus 324 divided by 8 squared, so 64. And we get something positive. Sorry about that. All right, so we have a local minimum here because we're going from negative to positive. Let's confirm that it's indeed an absolute minimum on this interval. Well, here I've got my minimum value, and to the left, the function is continually decreasing, and then to the right, it's just always going to keep increasing. Okay, it doesn't matter how it increases, it keeps getting larger and larger and larger. So that means this is not just a local minimum on this interval here, it's an absolute minimum. All right, so now let's take a look at what they were asking for. They were asking for the dimensions of the page, so we need the dimensions of the whole page. All right, so here, when we're looking for our answer, we have that the length of the page is going to be, well, remember, x plus 4. So I'm going to have to add 4 to this, so that's just going to be 11.35 centimeters. And then here, I'm going to find my y value, but then I'm going to add 6. So then my y value is 81 divided by 7.35. Okay, let's calculate what that is. 81 divided by 7.35. That gives us 11.02. And in order to find the width of the page, I'm just going to have to add, remember it was 3 on top and bottom, so I'm just going to have to add 6 to that, so that's going to be 17.02 centimeters. All right. So just to recap here, we kind of figured out that it was easier to work with this problem by letting x and y be the dimensions of the smaller rectangle, the rectangle that represents the printed area. And then from there, I could use those variables to write the area of the full sheet. Was able to use the information about the printed area to write in terms of one variable. And then I went through all my calculus to figure out my minimum values. All right, that's it for this one.